Let me welcome Zim Aberson for today. I'm very grateful to have him here and talk about dropsondes and hurricanes. Let me give you a little bit of his background. Zim got his master's, bachelor and master's at Penn State in meteorology, and his PhD in 2003 from University of Maryland in atmospheric sciences. Since 1988, he's been with the NOAA Hurricane Research Division.
Actually, I started in 1981.
Okay.
Off and on, so I've been there a long time.
It's a very long time, but 88 since permanent employee.
Yeah, that's when I got hired as a federal employee.
Exactly. His big research interest is hurricane research and forecasting. And just today I learned he's been doing, 180 flights into hurricanes?
180 penetrations.
180 penetrations. This is more turbulence that I wish to experience in my life. But he looks good, actually. I mean, I don't see any green shade. Zim has published over 40 peer-reviewed publications, over 50 conference papers and technical reports. And I see a bunch of faces in here who know him quite well. So I'm really glad to have him here. I was quite surprised. He has won a number of awards, presidential early career. Yeah, who would have thought? Yeah. Let me list them, please. Yeah, the Presidential Early Career Award, National Academy of Science, Kavli-Frontier Fellow, Department of Commerce Bronze Medal, National Organization of Gay and Lesbian Scientists and Technical Professionals, and a NASA Group Achievement Award. So congratulations, that's no small feat. Today's talk is about his personal experiences and lessons in hurricane research and the roles of dropsondes in that field, and I'm really looking forward to that. Please, Zim.
I actually got hired, started working at what is now HRD in 1981 as a high school student, and my first project was about dropsondes. So I'm still doing pretty much the same thing I got originally hired to do 30 some odd years ago. And I really like using dropsondes, especially the GPS sondes. So for this, I got to go back and look at some of the. Oh, geez. Is it on now? Is it on? Okay. So I actually got to go back and look at some of the earlier history of dropsondes, way back when soundings first were starting to be made. The first soundings were by kite. So it was during the late 1800s, and they would put the instruments on kites. And I just found out from Holger that they got up to, how high did you say they were? 10 kilometers with kites, and I had no idea that they could send kites up that high. And they discovered as a result of that, they discovered the tropopause by 1902. But most of the soundings were obviously much closer to the ground, so they didn't get very high. So they started to look at sending the instruments up with weather balloons. So there were some of the history is that Robert Bureau in France, he sent up one of these with a balloon in 1929 and radioed back the data. And then the next year, Molchanov launched an instrument, and he encoded the data in Morse code so that it was easier to send the data back. And that was considered to be the earliest radio sondes. But they didn't have wind with these. So after that, they started to track the radio sondes with theodolites by World War II, and that was the beginning of what we now consider to be the Raywin sonde. And later on, they automated it with automated theodolites, so they could follow them. At the same time, during World War II, a man named Colonel Joe Duckworth, he took a bet that he could fly his plane into the eye of a hurricane from the coast of Texas, and he did it twice that day. And it was the beginning of the era of hurricane reconnaissance. He went on to become what they call the father of instrument flight. He was very influential in all the instrumental flight that followed in the 50s to make modern air transportation possible. When he went out there, all the observations were visual. They looked out the window and they could see the waves, and they said, oh, the waves make it look like there's 40 knots of wind, and that was what the intensity of the storm was. There wasn't any other way to estimate what was going on in the storm. But starting in 1944, the Air Force and the Navy started regular reconnaissance, especially out in the West Pacific during the war. If you're familiar with Admiral Halsey, his troop transport got caught in a typhoon, and hundreds of sailors passed away in what's now called Admiral Halsey's typhoon. So they started regular reconnaissance to find typhoons out there, and then in the Atlantic they started it in the next year. So how do you measure the intensity of a storm? Well, back then they didn't know how to measure the wind very accurately, but they knew that the intensity was related to the low pressure. So they took these reconnaissance that they had, and instead of putting a balloon on them, they dropped them out a hole in the bottom of the plane, and they got the surface pressure. And that was the first way that they were able to measure the surface pressure of a storm that wasn't making landfall. And it turns out that we were able to identify this person. His name was John Michi. He worked for the Air Force and then later for what is now NOAA through the 60s and 70s. But the US military started to do this in 1949. We don't know exactly when they started because the documentation doesn't say, but sometime later in the year. In the 1950 reports, they have a list of the actual dropsondes that they released in all the typhoons. And in the Atlantic, in the first storm of that year, Hurricane Abel, they released some dropsondes in that, and the era of modern dropsondes started. So they did this pretty much every time they passed through the eye of a storm to get the surface wind. Well, that went on for a couple of decades, and later on the Omega navigation system came online, and that's a precursor to the global positioning system. And with that, they could get wind. So for the first time starting around 1970, we had what we call Omega dropwindsondes, ODWs, and I guess they call them Omegasondes here. And they were first used in the GATE experiment off the coast of Africa. And they gave us some amazing data in that area that we'd never seen before. So for the first time, we had profiles of wind and thermodynamic variables off the coast. The resolution was fairly coarse. About every 50 millibars we got points, and we didn't get winds very close to the surface, or we did not get any winds in clouds or rain. So it had to be in clear air, and fairly coarse measurements, but they were fantastic at the time. They'd never seen anything like that. So after GATE, Joanne Simpson, who's pictured here at the top, and Bob Burpee, who was the director, eventually became the director of HRD. At that time, he was the head of our field program. They got together and they were discussing dropsondes. And Bob Burpee knew that one of the reasons that hurricane forecasts weren't that good is because we had no data around the storms. We didn't know what was going on over those oceanic regions, so we didn't know what was steering the storms, where they were going to go, and we didn't even try to predict intensity at the time. So they got together and they decided, let's try to take the P3s out and fly around tropical storms or hurricanes and release the dropsondes and send the data off the plane and get it into the models and see what happens. So the first time we did that, 2 P3s in 1982. I got to be on the ground and collecting the data at the time. And at that point, they found an upper level low to the north of Hurricane Debbie that they had no idea was there. It didn't show up on satellite. And when they put that data into the model, it changed the forecasts. But it took a good 15 years after that, to actually get a statistically significant sample to prove that this actually worked. And we did that with this paper that was in the bulletin that Bob Burpee spearheaded, and they reduced the track forecast error 16 to 30%. So, and that was as large as just taking the plane out, they got as much improvement to the forecast as in the previous 20 to 25 years of modeling these things. So they thought it was a great idea to do this on a regular basis. NOAA went out and bought the G4, which is there with its new paint job. And at the same time, Omega was getting old and was being replaced. So we started using GPS. So Terry Hoke here and James Franklin, then at HRD, got together and wrote this paper showing the NCAR GPS dropsonde. And this is the start of one of the starts of modern era of hurricane science. It really revolutionized what we know about hurricanes. The citation on the AMS website says it's been cited 100 times, but I found over 360 papers. Lots of people don't cite the paper, even though they use dropsondes. So it's hard to find all of them. So we went out and we started doing the synoptic surveillance with the G4. And after a couple of years, we started getting improvements, but they weren't as large as we'd seen with the previous cases. And of course, in the ensuing 15 years, we started to get a lot more satellite data. So there was a lot more data out there. So it was harder to improve the forecast. But in this first paper that came out that I wrote, we started talking about not only improving getting these data, but making sure they get into the models properly by improving not only the models, but the data assimilation system. So we did some studies, and in one of those studies, by 2001, we were changing the data assimilation system. Here's the first time we used an ensemble Kalman filter to assimilate the data, and you can see when we use, up on the top here, when we use just the old type of data assimilation system with the data, we got something around the storm here. It strengthened the storm, but that's about all we got. But we got a lot more features when we use a much more sophisticated data assimilation system, and we actually improved the forecasts quite a bit. And that was by 2006, and ENKF is now used in partially in operations starting last year to assimilate the data. So it took about 10 years to get it into operations, but it's certainly the state of the art now. One of the other interesting things, at the time we thought that hurricanes were pretty much advected by the steering flow, but Krish's group at FSU, they used data from a field experiment for Hurricane Aaron off the, actually Hurricane, Aaron and Umberto and Gabrielle in the Atlantic during the CAMEX field experiments. They assimilated only the humidity data. And we didn't think that that would have a big impact, but it actually had a much larger impact on the track forecast than just the wind itself. And that surprised us. And for various reasons, the global models weren't assimilating the humidity at the time, but given this study and some studies that confirmed this, they started assimilating the data a few years later. And based on these results, Taiwan went out and got a plane similar to the G4, and they started developing their own targeting techniques and dropping sondes for around typhoons that were getting ready to affect Taiwan. And they've been doing that since 2004 very successfully. They're getting very large improvements as well. So we have regular surveillance in the Atlantic and in the West Pacific now as a result of this. But that was what they originally designed it for, but we found other uses for the sondes. Back in 1997, this is a schematic from one of Dalin Zhang's papers, one of his students, and back then we were getting away from the symmetric version of what a hurricane was, a circle, due to the Doppler radar data and what we'd found from the P3. But we still had a general idea of what a hurricane looked like. We had inflow at low levels, which at that point was thought to be below 1.5 kilometers all the way into the center. There was an eyewall updraft, which was generally believed to be gentle, 2 to 3 meters per second, all the way up, and upper level outflow. So there's the in, up, out circulation, and then there's some inward circulation at the top and some subsidence, which gives you a warm core and the low pressure at the surface. And by this time, we knew that there were dry downdrafts right at the inner edge, and there was some mixing going on at that interface, and that the strongest winds were at the top of the boundary layer, which was about 1.5 kilometers known at that time. So the first year we had the GPS sondes, it was a very inactive year, so we only had 4 surveillance cases. So we didn't have much use for them, for the sondes. But we took the P3s out to the West Pacific into Hurricane Guillermo, which is a Category 4 storm. And Mike Black was on the plane, and he realized that they were getting winds in the rain and in the clouds for the first time, which we couldn't get with ODWs. So he said, I wonder what will happen if we drop this in the eyewall. So they dropped one in the eyewall, and they got 78 meter per second winds, and they got thermo all the way down close to the surface, and they were surprised. So they pretty much bombarded the storm with Dropsondes after that on August 3rd. Unfortunately, this is the last day we could reach it, so we didn't have continuous measurements. But those are the first time we released them into the eye wall of a hurricane and around a hurricane. So what happened after that is NHC started getting these data. And they were like, wow, we can actually measure the surface winds for the first time. So they started putting in their reports by the next year. Hurricane George, which was Category 5, they measured winds of 134 to 150 knots at the surface, and they put that in their report. And they also discovered something interesting, that the winds at the surface were about 20 to 30% below those at flight level, and that this was different than what they expected. So what they were doing for intensity before that is we flew at 10,000 feet, they got the wind measurements, and they said, oh, it's about 80% at the surface, and that's what the intensity is. But the Dropsondes made us realize that's not what's really happening. And that led to a huge project that's been going on for about 15 years, the Atlantic Hurricane Reanalysis project that Chris Lanzi is running. And part of that is a reassessment of even more recent storms, and they upgraded, as a result of this study, they upgraded Hurricane Andrew to a Category 5 at landfall, which they didn't think it was before. So NHC was using these surface adjustments, and they used 80 to 90%, but they found that this was incorrect, and they came up with some statistics to look at what the intensities of the storms were if the sondes didn't reach the surface. What we were getting from the flight level was giving us a better estimate of what the actual intensity of the storm was. And this paper, paper here, Franklin, Black, and Valdez, they pretty much are using that now still as the baseline for what they're using for intensity. So it started to be used in operations almost immediately by 1998, but very quickly people realized that they could use these sondes to validate data. So we have cloud motion vectors from the satellite that SIMS up in Madison puts together, and they decided that they could validate their low-level and mid-level cloud motion vectors using the Dropsondes, and they found that they were very good, and they wrote something nice about the sondes in the paper. We have an instrument on the plane called the step frequency microwave radiometer, which looks down from the plane and looks at the ocean surface and gets an estimate of the wind speed at the surface. And how do you validate that? Well, now we have the Dropsondes that are reaching the surface, so we can validate that. And it's ongoing. There's some issues at the lowest wind speed, actually. But at the highest wind speed, we can get winds of almost 200 knots at the surface validated with the sondes. So this was also a great tool in validating the SFMR data. And also surface winds from scatterometers, from QuickScat and the SSMI instruments, and they were also used by these scientists to validate those instruments. So the Dropsondes were really great to validate all these different types of instruments that we have from satellite and from aircraft. So we know how accurate they are. But Jeff Keppert from Australia in the late 1990s got a hold of the data from Hurricane Mitch and Hurricane George. And he noticed all sorts of very interesting features down near the surface. Some boundary layer jets that we'd never seen before, and low-level wind speed maxima within the boundary layer. And he tried to compare that. Oh, I have a bug here. He tried to compare that to some of the boundary layer models that he had experience with, and found that they weren't doing a very good job. So he decided he had to improve those models. But one thing that came out of this is that they found that some of these wind jets were so low, down below 100 meters, that they had to change some of the warnings for people in landfalling regions. A lot of times I used to tell people to vertically evacuate, go up in buildings, 50 floors high if possible. And some of the cities along the coast did have buildings that high. And given this, they knew that the winds could be 20, 30 knots higher at those altitudes. So they no longer recommend people vertically evacuate. And this has great applications in regions like New Orleans, Miami, Houston, and in Hurricane Matthew, it was important in Jacksonville. And he started looking at the data for those two storms I named, and then two weaker storms. George and Mitch were both Category 5. Danielle and Isabel were both much weaker, and he found that the boundary layer was different in all these different storms. It was a lot more complex than he thought. And instead of the inflow being at below 1.5 kilometers everywhere all the way in, it got lower as you got closer to the center, and the jet was different on the different side of the storm. We always thought that the winds were strongest on the right side of the storm, but these jets turned out to be strongest on the left side of the storm. And the boundary layer models that we now use reflect a lot of this data. One of the issues that we have always had is that we weren't able to measure things like surface stress, drag coefficients that are important for air-sea interaction. It's the ocean below that's giving us the energy for the hurricane, but how does that energy get into the atmosphere and into the hurricane? In the models, we used to assume that at low wind speeds, some of these values changed in a certain way, and we just extrapolated. And now with measurements close to the surface and at high resolution, we started getting these data at 2 hertz, so every about 5 meters, I think. And now they're up to 4 hertz. And so they started getting much better measurements. We still don't have a perfect idea of what's going on, but it's a lot better than we had before. We modified the parameterizations, and some of the forecasts are much better as a result. But this was the first time we got these measurements at such high wind speeds in a paper that was published in Nature by a group led by Mark Powell. And Jun Zhang, who is not a meteorologist, but he's a marine physicist, he now works at HRD. He wrote a whole bunch of papers looking at some of the parameterizations, and he came up with the paradigm of looking at the data, looking at what's going on in the model, revising the model, going back and forth to improve the model. And a lot of these parameterizations, each one of these represents a change in the parameterizations that are going into the NOAA model, which is HWRF. And each one is leading to a pretty good improvement in the intensity forecasts. Some other scientists have been looking at the different wind profiles, and as I mentioned, the jet gets lower as you get closer to the storm, and the profiles, the wind profiles with height and the radial wind changes in the different quadrants of the storm, which we hadn't seen before. So that was the first time we'd seen that. But not only that, we're getting for the first time high-resolution thermodynamic data in the storm. And Gary Barnes out in Hawaii with his students wrote a number of papers looking at the different thermodynamic profiles and the energetics in the boundary layer, especially near landfall. He had some experiments where we actually flew along some trajectories and dropped sounds along the trajectories to see how the energy changes as the wind spirals in toward the center. And he found a lot of atypical profiles, and also that there is a lot more energy in the low-level eye than was expected from our current understanding. And some other scientists ran with that a little bit later. As a result of other NASA experiments, the P3s generally fly at 10,000 feet. So we fly at 700 millibars and we get data below that. But as part of the CAMEX experiments, they took out the DC-8 and the ER2 and dropped sounds from 65,000 feet. So we finally, for the first time in the early to mid-2000s, got the full profiles all the way from the above the tropopause down to the surface, and for the first time we got very good, much better ideas of the dynamical and thermodynamical aspects of what's going on in the storm, including the warm core and storm asymmetries that we didn't have before. So by the early 2000s, we were really getting quite a different look at what was going on in the hurricane. And this was a schematic for a very strong storm, Hurricane Aaron, which was Category 3 on September 10th, 2001. But for the first time, they also started looking at what was going on in very weak, highly sheared storms, and they were able to confirm some of the theory and model work that had preceded. But this was the first time that any of that was actually seen from those high altitudes. In addition, the Canadians started flying hurricanes, and they flew systems that were making landfall up near Canada, and they found when storms were moving over colder water, they found some very interesting features, whereas in the tropical cyclone we had these low-level jets. They had a low-level jet at 500, about 500 meters above the surface, but 70 meter per second winds, 500 meters above the surface, but the surface winds were about 45 meters per second. And in a standard hurricane, that really, that decrease with altitude doesn't happen. It was because of the cold air. So they were able to look at the intensity of a hurricane that was going to affect high latitudes and change their forecasts accordingly. In this case, this storm did make landfall in Newfoundland as a Category 1, but it was Category 1 at the surface, but it was almost Category 3 just above the surface. They had, a couple of years later, they had Hurricane Jose, which made landfall, Juan, which made landfall in Halifax, Nova Scotia as a Category 2, but they had winds above that hit the mountains behind the city that were much stronger, and they were able to measure those. Matt Easton in North Carolina, he started looking at some of these data to see whether the updrafts that we were getting, the upward motion in the eye wall, whether that was caused by buoyancy or whether it was mechanically forced. And that will tell you how much energy might be released to force the circulation, and he found that there was some buoyant updrafts in the storm. They didn't tend to be very strong, but they were related to the shear. So if you were looking where the shear vector was, down shear seemed to be where most of the buoyant updrafts were, and there were convective downdrafts up shear. So started to look at some of the asymmetry related to the storm. And John Molinari's group at Albany, he started to look at the helicity and the cape related to this, and he found possibility of supercells in tropical cyclones based on some of the soundings that he looked at in the 2000s. And not only were supercells possible, but also when we flew in Hurricane Isabel when it was Category 5, we were dropping these 8 to 12 sound sequences as fast as we could to see what was going on in the eyewall. And Jeff Smith, who is the lead dropsonde person at AOC, he was running the drops, and he called out that one of the sondes was moving up, and he'd never seen that before. And it turned out that this sonde moved up a couple of 100 meters, got caught in a strong updraft that had to be at least 15 meters per second, and it turned out to be above 20 meters per second. And it moved up by a couple 100 meters and then moved down. The horizontal wind speed was 107 meters per second, which at that point was the strongest we'd ever seen. But what's going on? We have temperature in this feature cooled a couple of degrees. It was right at the top of the saturated layer. The wind direction changed quite a bit. So we hypothesized that we had a mesocyclone on the interface of the eye and the eyewall, and Mike Montgomery had a theory of mixing between the eye and the eyewall, which can take that high entropy air that was found earlier in the low-level eye and push it into the eyewall and increase the energy of the storm. It's still questionable whether that happens or how important that is, but we started to see these very small-scale features that we never knew could even exist in the storm. And it was also hypothesized by us and by Pete Black that these features, if they occur further down, close to the surface, if you get them in a downdraft, they can go down to the surface, and that could be responsible for some of the catastrophic wind damage that we saw at the landfall of Hurricane Andrew in Miami in 1992. We've since looked through the entire catalog of hurricanes, of hurricane dropsondes, and we found about 200 of these sondes that have actually moved upward, including one in Hurricane Patricia that moved upward more than 1,000 meters before it lost telemetry and disappeared. So for all we know, it's still up there flying around. But that's the most spectacular one. It was over 100 meters per second horizontal wind and over 20 meters per second vertical velocity upward. We're also now starting to catalog the largest downdrafts, and we're finding downdrafts up to 15 to 20 meters per second. Not quite as strong as the updrafts, but they're there. George Bryan is here, and Daniel Stern. I started with Daniel Stern when he was an intern at HRD, and then he came here and was working with George and started looking at these upsondes. And they not only we not only cataloged them and figured out where they are in the storm, but they're in the process of confirming that the very high resolution models can produce these. And at the last hurricane conference, Daniel showed some dropsonde profiles in their model and some real dropsonde profiles, and you can't tell the difference. The only way I could tell the difference is I knew what the real ones were. But the model looks exactly like what we're seeing with the dropsondes. So that's very encouraging. But you need to run at 60 meters resolution to get that? Yeah. So not going to be in operations anytime soon. Bell and Montgomery and Abarca and Montgomery and Scott Brown, they started looking at dropsondes in some of these storms that were undergoing eyewall replacement cycles. It's still, we don't fully understand how these happen, and we don't know how to forecast them. We've bombarded a few storms that were undergoing eyewall replacement cycles with sondes, and they're learning that as expected, as we thought, the radial wind was coming into the secondary eyewall and not going further in and producing the secondary eyewall. So you were getting the convergence seen just inside both of the eyewalls, but eventually the outer one chokes off the inner one, as our paradigm suggested. But it's very good to see these in the data as well. And then they also started looking at a lot of the dropsonde profiles and looking at the gradient wind imbalances and how that relates to intensification. Also, they found signs of unmixed boundary layers several hundred kilometers outside of the center. And we're discovering all these things. We don't know what they all mean yet. For example, we don't know what this unmixed boundary layer is. We don't know whether these very extremely strong updrafts in the eyewall and extremely strong downdrafts, whether they're just there or whether they have an important, they're an important piece of the puzzle in intensity change. But we have to keep studying them. Matt Easton's group started looking at the dropsondes and looking at what's going on in the outer rain bands, because that tends to be where tornadoes happen. So he's looking at whether we can predict whether tornadoes are going to be happening in the outer rain bands of storms as they make landfall. And some larger scale features. Jason Dunyan started looking at the sondes, and he realized that something we've been using since the 1950s, which is called the Jordan mean sounding. In the 1950s, Jordan took soundings from San Juan and a couple other stations in the Caribbean and made an average of them, and it's called the Jordan mean sounding, and it's what we've been using forever. What's going on in the tropics? This is what the tropics looks like. Well, he found that that's not what the tropics looks like all the time. In here, you can see the black is the Jordan mean sounding, but about 3/4 of the time you get the solid blue line here, which is a moist sounding. But in the Atlantic, we have these Saharan air layers that come across from the Sahara, and about a quarter to a third of the time we get this very dry sounding. And if you pretty much average these two soundings together, you get the Jordan mean sounding. But the Jordan mean sounding was used in a lot of modeling studies as the background. And if you use the new Dunyan soundings, you get completely different results. And he's also started looking at the impact of the dry air on these from these Saharan air layers when they get into hurricanes or some of these incipient systems, easterly waves. What happens? And sometimes this dry air can get into the core and weaken these systems. And we used to look pretty much only at whether it was warm water and whether there was shear, but now we know that we have to look at whether there was a lot of dry air in the area as well. And a lot of those measurements are from the dropsondes. And there was a field experiment off the west coast of Africa that NASA conducted, NAMA, and for the first time we started looking at some of the, first time since GATE actually, we started dropping sondes and getting very high resolution and very good coverage of what these systems look like as they come off the coast of Africa and they either develop or they weaken as they move across to the west. And they found that there really isn't one type of easterly wave. There's all different sorts of easterly waves, and there's a northerly part and a southerly part that we now track across the Atlantic, and mainly look at the southerly part. But every so often, the northerly part can develop into a tropical cyclone. And then some scientists from either the University of Miami and Ed Zipser's group, they started looking at the sondes and the data in relation to whether disturbances are going to develop into tropical cyclones or not. So they were able to separate developing and non-developing and look at the dropsonde data and have come up with some ideas as to whether we can tell whether a system is going to develop or not. And finally, not only developing, but also looking at how tropical cyclones decay over warm water. Gary Barnes again looked at systems as they were moving toward the cooler water of Hawaii and how the systems spin down, somewhat like what the Canadians were looking at. But the water isn't as cold around Hawaii, but the systems do tend to weaken quite rapidly right before they hit Hawaii. At least they did back then. Hawaii has since gotten hit by a couple of hurricanes that didn't weaken as fast as they expected. And not only do we have those, but we're starting to look at how the outflow, so it's not only the in, up, but now we're starting to look at the out, looking at what's going on in the upper level outflow and turbulent layers. Molinari's group found that there were turbulent layers in the outflow, and that the cloud structure up there creates its own stability profile that impacts how the outflow is influencing the intensification or the weakening of the storm. And these are new papers that just came out in the last couple of years. There's some more recent work. Jun Zhang is still working on his project of improving the models step by step, and he's come up with a paradigm of how the boundary layer recovers. If you get a dry downdraft, the air over the surface of the water is dry. It tends to be warm, but you're surrounded by all this warm water and warm, moist air. How does the boundary layer recover? How do you get the convection to how does this impact the convection? Does it slow down the convection? How does the boundary layer recover and the convection start again? Or is this like a wave number one asymmetry around the storm with the updrafts down shear and the downdrafts, the warm, dry downdrafts down shear? So this is work in progress. Some data assimilation work that I'm working on. Right now we send the data off in sort of a low resolution form. And if we do that, we don't know exactly where the sondes are. And that wasn't a problem when you had a 25 kilometer model, but now HWRF is run at 2 kilometer resolution. So if we use the data that we send off the plane as it's sent off the plane, if we assimilate data into a hurricane model, this is Hurricane Edward from 2 years ago, Category 3 hurricane. You get these really messy features in the surface pressure, very strange features in the wind speed and in the low-level thermodynamics. But if you can calculate where the sonde actually is and put the data in the model correctly, this is what you get. You actually get something that looks like a hurricane. All the operational models, they do this. So actually, all the operational models, they just take the dropsondes within 111 kilometers from the center of the storm and say, nope, we're not going to assimilate them and get rid of them because it creates these sort of features. So we want them to start using these data, so we hope that we can get these techniques into operations sometime soon. We're seeing some very strange features. Hurricane Emily in 2005. Here's an eye sounding. Never seen an eye sounding like this. There's all these very, very unstable layers in the middle of the eye. Almost zero horizontal winds, so we know we're in the middle of the eye. We're not near the eye wall. We had a 10 meter per second updraft in the middle of the eye. We looked through all the sondes. We found no updraft or downdraft greater than 2 meters per second, except for this one. This is an extreme outlier. But also, here's the temperature in the eye wall. So in this case, the temperature in the eye wall was a lot higher than the temperature in the eye. Not only was it a lot higher, it's 8 degrees higher. And we've never seen anything like that either. So we don't know what's causing that. We're just learning what's going on here. And we know the extreme circumstances that the dropsonde works. In Hurricane Felix, we flew into the eye. We got a 31 meter per second updraft followed by a 13 meter per second downdraft about 20 seconds later. I think the plane underwent 6G at that point. And it turned out that right when we hit that 31 meter per second updraft was when the dropsonde operator pressed the button, and the sonde went out right there. So we have a sonde, and this paper is in review looking at this mesocyclone and what it did at the time in the hurricane. But we're seeing these features, but we still don't know whether they're important for intensification. They're almost always in Category 5 hurricanes, so they're not in intensifying storms, but are they important for maintenance of the extreme intensity? Don't know yet. So one of the things that Holger asked me to do was, what's the future of dropsondes? What can we do? Well, one of the things we need is very high resolution data. Whether a dropsonde can do this, I don't know, but we're trying to nail down turbulence and coefficients in very high wind speeds. The P3 gathers data at 40 hertz at flight level, but we no longer fly low enough to make a difference to measure things near the surface. I did fly in Hurricane Isabel and hurricane force winds 170 feet above the surface of the ocean. So we got some data, but we're not stupid enough to do that anymore. So we need some other instruments that can get that. Sea surface temperature. It would be great to be able to get sea surface temperature, and I know there's now IR sondes that are starting to get some of this data, and we dropped a whole bunch of those 2 years ago in Hurricane Edward, and we're evaluating that now. But we also want oceanic profiles, what's going on with the temperature and the salinity and the currents below the surface. I don't know if this is something that can be gotten from dropsondes. One thing we really need is the atmospheric and the sea profile, ocean profile at the same place. When we drop the BTs, they're heavy, they're big, they drop down. When we drop the sondes, sondes are horizontal profiles if you have more than 15 meters per second of wind. So the sonde doesn't land near the BT, and we have to pretend that they do in order to do any of this work. Cloud physics. We no longer fly in the mixed phased region because we found that it hurts the plane too much. So we aren't getting any of the cloud physics in the mixed phase region of the storm. We haven't had any since 1980. So it'd be really neat if we could come up with some sort of instrument that we could drop through from high altitudes and come see what's going on in the clouds in the mixed phase region, whether it's ice or water or the different types of particles. And on my wish list, this isn't really a sonde thing, but with the Doppler radar, we have a 3D view of the kinematics of the storm, but we still have very few measurements of what's going on with the temperature and the humidity in a storm. If we can come up with some way to get a lot of observations of all of this in one case, that would be great. Here's I wanted to finish, that was pretty much finished, but this is some of the data with the IR sondes, preliminary data where they dropped the IR sondes, which looks down and measures the infrared radiance coming back from the surface, and they also dropped BTs to get the surface temperature. So this is a comparison of the surface temperature from the sonde and from the BT, and they're finding that these sondes don't work in rain, but they work in clear air. So we're back to what happened with the old ODWs. So if we can figure out a way to get sea surface temperatures in the eyewall in the rain, that would be great. So with that, I'll finish.
Thank you very much for a very interesting talk, and I open it for discussion. Any questions?
How well do you think you can get the exchange coefficients at low altitude? Because obviously you can measure the position of it, but if you have lots of sea spray, you have other momentum transfer. So will it really truly give you the drag coefficient?
They're estimating it. The values that they're getting are all over the place. And so, whether we can really nail that down, with this data, probably not. We probably need a lot of other measurements to get that. But That's the only thing we have right now until we have some other instruments, maybe an unmanned aircraft or something else. We can't fly down there. So we'll see how that goes.
Kind of a question on the history of dropsondes, more so than meteorology. These early pictures you showed, were they dropsondes on parachutes, or were they just ballistic? They just dropped this device that just went plummeting down.
I don't know. I didn't see any pictures that had the parachutes on them. And there's a couple of people around who worked on them, so I have to talk to them and find out exactly what it was. Yeah.
I wonder if you could elaborate on what an unmixed boundary layer is, because in my perception, by definition, a boundary layer is mixed.
Well, what they're finding is that there's a lot of different boundary layers. There's a temperature boundary layer, there's a frictional boundary layer, there's a moisture boundary layer, and they all have different levels. They're not the same in a hurricane. So that it was unmixed in terms of theta E. So there was a boundary layer in terms of the frictional boundary layer, I think. But that frictional boundary layer with the wind wasn't mixed in relation to temperature and humidity as they expected.
So you mentioned that something isn't working here in the rain. Is it the IR sensor or the sonde or both?
Yeah, I think it's the IR sensor. I think it looks at the surface and it's measuring what's coming back, but it has to go through the cloud and the rain and everything, and that's...
Only use the last 20 meters of it for the surface temperature.
Yeah, I mean, you could see that the red ones just aren't working, and I think, I don't know exactly what was going on with these. I don't know if...
If you have droplets on the lens, you measure the temperature of the water.
Yeah. Yeah. They dropped a whole bunch of these more in Matthew, so they have more data, but it's a first step.
Any other question?
Sure, I always get hit up.
Wait there.
I always get hit up with the question with the cost of the dropsonde. It's a disposable device and they're expensive. So the question I've always proposed to different people that use the dropsonde data is, well, what if I cut the cost of the dropsonde in half so you could drop twice as many, but now your thermodynamic sensors are, say, 4 times as bad in terms of accuracy. So it's a trade-off of cost versus performance.
Mm-hmm. We have a lot of different experiments. So, we might want a whole bunch of different types of sondes. If we're looking at air-sea interaction, we might want something with very high resolution in the thermo and very accurate, but we only may want, a few tens of them. And there may be some where we're looking at, some other features where the thermodynamic aspect isn't important, we want the winds, So it depends on exactly what we're looking at. And we're looking at so many different things. And a lot of this research is just people looking at the sondes and finding things, not going out looking for looking at something specific. Just, this sounding looks really interesting. What's going on here? So there's a lot of serendipity in all these data, and we have tens of thousands of these now. So they're great.
Hi, Sam. You had shown an example of the impact of the assimilation of the dropsondes from N SEP, I think back in 2005 or so. Yeah. So that was one of the larger dropsondes. I know that N SEP isn't currently assimilating the data from the miniature dropsondes. So I was wondering if anyone at HRD or anyone that you know of, have you done any research looking at the impacts of the European models that are assimilating the data from the miniature sondes?
Well, first of all, N SEP is assimilating the Global Hawk dropsondes. So those are the mini sondes, right? In HWRF, right. So they're not putting them in the global model. Mm-hmm. HRD is using our data assimilation technique, and there's actually a workshop at HRD Friday where they're going to present some of those results. So I don't know what they are, but they are testing the impact of the Global Hawk dropsondes in HWRF.
Do you know if that'll be like video conferenced or anything? Is that available?
So I'm kind of leading that all.
Oh.
Passing
Okay.
along the information.
Fantastic.
Any other question?
So I've been very interested in using the sondes in the surface layer, the lowest 100 meters, to work on this flux issue and transfer coefficient. And I've always been troubled by the issue of, do the sondes actually resolve these sharp gradients? Or maybe I should say, at what point do they quit resolving them? And that's a very important issue, but I haven't really seen anything on the literature about that. Curious if you know of something.
That's going to depend how you process the data, and I don't know what the limits are. When we process the data, in operations, we use a 10-second filter. In research, we use a 5-second filter, and that's going to filter a lot of these gradients out. I don't know, depending on what you want, you might be able to use the raw data looking at the gradients, not at the actual numbers, but I think you might need to talk to the engineers a little bit who are here about what the limits are.
But you can see what I'm driving at. These drag coefficients people have going down at high wind speed is the same thing as saying the wind gradient measured by the sonde is not as big as it could be.
Yeah.
And you're falling, you got to go from 50 meters a second to zilch in 50 meters. Mm-hmm. Can you do that?
Well, and one of the things we've been talking about is in a hurricane, you have all these waves. So what's the surface?
That's even worse.
Yeah. So I was mentioning that we have some sondes that look like in the last 2 points they're rising, and are they really rising? Are they going up the crest of a wave, or is it some sort of an instrument error? A lot of the stuff when you're looking at the very small scale, I don't know whether you can look at individual, sondes, or you have to composite them, and what the limits of all that are. That's really difficult.
One of the papers Sim cited was by David Richter, came out, I think, earlier this year or late last year. They were asking a lot of these questions using some of the model simulations that Sim mentioned also. And I think their overall conclusion was one Sim said earlier, is that there's a limit to what you can do with these sondes. And we need probably some in situ tower data to address some of the questions you're asking.
Get the oceanographers to put some towers out in the ocean. Yeah.
Okay. Any other questions? One last question. Here, Nick.
I'm just going to ask an off-the-wall question here. If you had a magic sonde that could measure anything, what would it be measuring, and what are you looking at?
Yeah, Pete Black has an experiment called the meat experiment. Measure everything all the time. And that's the magic sonde that we want, something that can stay up for a long time and measure everything everywhere. Like I said, a lot of the stuff that I look at is just serendipity. I'm doing a lot of work with the data assimilation and looking at the impact in the models. But then when I find some interesting sondes, interesting events, like when we flew through Hurricane Felix and we rose a couple of 100 meters in a couple of seconds, that's pretty interesting. So I start to look at that sort of stuff. But a lot of the stuff that we're finding is stuff that we didn't expect and weren't looking for. And so we just keep measuring a lot of stuff. We'll find a lot more, and eventually we'll figure out what the impact of all this stuff is. There's a lot more to learn.
Okay, let's give Zim one last round of applause.